In the silent exchange between our industrial world and the sky above, a complex chemical process is unfolding. This is the story of acid rain. For decades, we have watched our horizons change, but the most profound changes are often those we cannot see until the damage is irreversible. Welcome to this comprehensive 20-minute exploration. Today, we journey from the microscopic chemistry in the clouds to the impacts on our streets. We will examine how everyday industrial activity and sudden catastrophes like oil depot explosions reshape our atmosphere and our very health. Our journey begins with the pH scale, the scientific measure of acidity and alkalinity. It is the fundamental key to understanding this challenge. The scale is logarithmic, meaning each whole pH value below 7 is 10 times more acidic than the next. Small numerical drops mean massive chemical changes. Pure water has a pH of 7, but even unpolluted rain is naturally slightly acidic at 5.6 due to atmospheric carbon dioxide forming carbonic acid. But when we talk about acid rain, we mean precipitation with a pH between 4.2 and 4.4, a concentration powerful enough to damage sensitive life forms. Wet deposition is what we typically recognize: acidic rain, snow, fog, and hail that fall directly from the atmosphere to the Earth's surface. Dry deposition involves acidic particles and gases that settle on surfaces during dry periods, often building up until they are washed away. To solve this problem, we must first look at the precursors, the gases that set this complex chemical process in motion. Sulfur dioxide, or SO2, is the primary ingredient. It's released in vast amounts when we burn fossil fuels like coal and oil for electricity and heat. Coal often contains significant amounts of sulfur. When burned, this sulfur combines with oxygen to create sulfur dioxide gas in the flue. Nitrogen oxides, or NOx, follow close behind, primarily produced by the high-temperature combustion found in modern internal combustion engines. Once in the sky, these gases don't stay in their original form. They undergo a rapid and violent series of oxidations and chemical transformations. When sulfur dioxide reacts with water vapor, it transforms into sulfuric acid, a clear, corrosive liquid that is incredibly stable in the air. Similarly, nitrogen oxides react with atmospheric moisture to produce nitric acid, further lowering the pH of the resulting precipitation. Sunlight acts as a powerful catalyst, providing the energy needed to speed up these chemical reactions and increase acid levels. Where do these millions of tons of acidic precursors come from? The scale of human emission is truly staggering globally. Coal-fired power plants remain the single largest source of SO2. Burning coal releases sulfur that was trapped for millions of years. On the world's roads, nitrogen oxides are a constant byproduct, released by every internal combustion engine in our global fleet. Industrial manufacturing and oil refineries also play a significant role, adding to the total load of acidic pollutants in our air. Even global shipping contributes, as large vessels often burn high sulfur fuel, releasing precursors far out at sea and into the wind. Winds can transport these pollutants for hundreds of miles. This means acid rain is often a problem for regions far from the source. The consequences are most visible in the natural world, from high mountain streams to the depths of ancient, fragile forests. In aquatic environments, acid rain disrupts the delicate balance. When the pH drops below 5.0, most fish species begin to struggle. Acid rain leaches the toxic aluminum from the soil. This aluminum is dangerous to fish, as it clogs their gills and leads to suffocation. At pH 4.0, almost all aquatic life is lost. Entire food chains can collapse, leaving lakes clear but biologically dead. On land, acid rain strips essential nutrients like calcium and magnesium from the soil, minerals that trees need to survive. Without these nutrients, trees become vulnerable to drought, cold, and pests. Forests across the globe are slowly declining. Even our stone history is at risk. Acid rain dissolves the calcium carbonate in limestone and marble, melting away historic monuments. While acid rain doesn't burn human skin, the air pollution that creates it definitely does. Let's look at the direct human health link. The danger isn't the rain itself, but the gases, SO2 and NOx, which react to form fine sulfate and nitrate particles in our cities. These tiny particles, known as PM2.5, are small enough to pass deep into the lungs and even enter the bloodstream directly. Once inside, they cause inflammation and oxidative stress, irritating the respiratory system and making breathing increasingly difficult. Exposure to these pollutants is directly linked to increased cases of asthma, chronic bronchitis, and other long-term respiratory diseases. Beyond the lungs, research shows these fine particles can also trigger heart attacks and strokes in vulnerable populations over time. The health costs of acidic air pollution are measured in billions of dollars and thousands of preventable hospital admissions every year. In many cities, these pollutants create a persistent haze, impacting the health of millions on a daily basis. We see this in air quality alerts. Monitoring programs allow us to track these levels, providing critical data for public health warnings during high emission periods. Beyond daily industrial emissions, specific catastrophic events like oil depot explosions can create sudden, extreme acidic risks. When oil storage facilities explode, they release concentrated bursts of hydrocarbons, SO2, and nitrogen oxides in a matter of minutes. These massive plumes trap huge amounts of heat and pollutants, creating their own localized weather systems high in the troposphere. The soot and pollutants can create black rain, a phenomena where precipitation is visibly contaminated with hazardous industrial residue. This rain falls as a toxic sludge, coating cars, windows, and plants in a layer of soot and concentrated industrial acids. For those caught in the storm, the rain is a mixture of water and concentrated pollutants, falling as a hazardous industrial byproduct. The volume of sulfur released can lead to localized rainfall with a pH as low as 2.0, approaching the acidity of lemon juice or vinegar. In these extreme cases, the rain can cause chemical burns to the skin and severe, immediate respiratory distress if inhaled by people. These events require immediate emergency response and public health warnings to protect the local population from direct exposure. While the risks are significant, we have developed powerful technologies to reduce these emissions and protect our atmosphere. Technologies like flue gas desulfurization or scrubbers can remove up to 95% of sulfur dioxide from power plant emissions. In vehicles, catalytic converters have been a game changer, drastically reducing the amount of NOx released into our city streets. The transition to clean energy sources like solar and wind is eliminating the primary sources of acid rain precursors altogether. The electrification of our transportation systems is the next great step in ensuring that nitrogen oxides no longer pollute our skies. Global agreements and strict emission policies have proven that scientific understanding can lead to real environmental recovery. Acid rain is a reminder of our impact on the sky. By understanding the chemistry, we can continue to clear the air for future generations. Stay informed, monitor your local air quality, and support programs that safeguard our atmosphere. Thank you for watching. Acid rain leaches toxic aluminum from the soil. This aluminum is dangerous to fish as it clogs their gills and leads to suffocation. At pH 4.0, almost all aquatic life is lost. Entire food chains can collapse, leaving lakes clear but biologically dead. On land, acid rain strips essential nutrients like calcium and magnesium from the soil, minerals that trees need to survive. Without these nutrients, trees become vulnerable to drought, cold, and pests. Forests across the globe are slowly declining. The soil chemistry is fundamentally altered, reducing its buffering capacity and making it less supportive of plant life over many generations. Even our stone history is at risk. Acid rain dissolves the calcium carbonate in limestone and marble, melting away historic monuments. Metal infrastructure is also accelerated by acid rain, leading to increased rust and the need for expensive repairs on bridges and buildings. While acid rain doesn't burn human skin, the air pollution that creates it definitely does. Let's look at the direct human health link.